Energy diagram is a systematic representation of the energy changes that we see in a reaction. So what we see in an energy diagram is the energy versus the progress of the reaction or the reaction coordinate. So for example, if I draw it here, what we will have here is the energy, and that is often represented by either the enthalpy or the delta G. Because remember that because the entropy term is usually negligible, the delta G is equivalent to or it's very similar to the enthalpy. So in here we have the energy, and here we have the reaction coordinate. And so the reaction coordinate represents the progress of the reaction. So here we have the starting materials, and here we have the products. So if this is the energy of the starting materials, the energy of the products could either be high there, or it could be low like that. So it's just a representation of the energy relative. So the energy of the products, how is it relative to the energy of the starting materials? These are not necessarily absolute values. These just tell us if the energy of the products is higher than the energy of the starting materials, or the other way around. And so what we're going to see is the starting materials go into the products, and the way this is going to be represented is by either showing a curve like that, or if the other reaction happens, then it will go like that, right? So it depends on where our products are going to be. And we're going to explore in this chapter what it represents for an energy diagram to show the starting materials in a lower energy than the products, or the starting materials to be in a higher energy than the products. Some other elements that we can recognize here is this energy right here. It's called the activation energy, and we represent it like that. And so that's the energy that we need to climb this mountain, if you want to call it. So this is the energy that we need for the reaction to reach up to this point, and then at that point the reaction starts becoming products. So this maximum of energy is what it's called a transition state. Okay, and so we're going to explore each one of these elements further. So the difference between the starting material and the product's energy, it will be this one in this case, that is the delta H. So in some cases, that delta H will be a negative value, meaning that the reaction will be exothermic, or that value could be positive, and remember that that means that it's an endothermic reaction. The energy difference, so the energy from the starting materials up to this maximum right here is the activation energy, and here at the top we have the transition state. The transition state is, it's not something that we can isolate in the lab, but it looks something in between my starting material and my products. So if you have a reaction where A, B transforms into B, C, right? What happens is that as that AB bond is being broken, the new BC bond is being formed at the same time. And so we represented in between brackets, just like here, and using this double dagger sign that indicates that that representation right here is a transition state. So as one bond is being broken, the other bond is being formed, and that happens at the maximum of the curve. So imagine it here. So we have the energy versus the reaction coordinate, and here we have a reaction happening. So the CBr bond is being broken and the CCl bond is being formed. And this transition state looks like something in between where one bond is being broken and one bond is forming. So here we're going to see some of the examples of these curves. So in this particular example, we have the starting materials here, and here are the products. And the activation energy, which is the energy that it takes the starting materials to reach that transition state, is very high. So what that means is that we're going to have a slow reaction. Because the difference between the energy of the starting materials and the energy of the products, it ends up being a positive number, meaning that the enthalpy is a positive number, then this will be an endothermic reaction. This reaction is not favored and it doesn't happen spontaneously. What happens, we need to add energy for this reaction to actually proceed. The second case that we're going to see right here is a reaction where my starting materials are have higher energy than the products. The result of this is that the enthalpy ends up being a negative value. And when the enthalpy is a negative value, this reaction is an exothermic reaction. So we don't have to put energy into the system. The system actually releases energy when this reaction proceeds, so that's favored. And then we have a high activation energy, which is this value right here. The activation energy is high, meaning that this is going to be a slow reaction. In this example right here, our starting materials energy is lower than the energy on the products, right? So if my products are here, then that means that this reaction will have a delta H being positive. And so if this delta H is positive, means that this reaction is endothermic. So for this reaction to actually proceed, we need to add energy to the system. And because the activation energy is a small value, it means that this reaction will be fast. And finally, we have an example in which the activation energy is small, but the difference between the energy of the starting materials and the energy of the products ends up giving us a negative delta H. And so that will be an exothermic reaction. So it's very important that you differentiate what kinetics and thermodynamics means. Kinetics tell us about how fast is this reaction going to proceed. So we can know the rate of the reaction, and that is based on the activation energy. So remember, if we have a small activation energy, the reaction will proceed fast. And if we have a high activation energy, the reaction will be slow. What thermodynamics tell us is we look at the difference between the energy of the reactants and the energy of the products. When that value is a negative value, then that means that the reaction will be exothermic. But when the difference is actually a positive number, then that reaction will be endothermic. And we've seen so far reactions that proceed in one step only, but we will see other reactions that will happen in two steps. And so when a reaction happens in two steps, what we're going to see is a energy diagram that will look like this. So we have the energy, here we have the reaction coordinate, and we will have the starting materials and the products. Right? Let's say that this reaction is going to be an exothermic reaction because the energy difference between the starting material and the products will end up being a negative value, right here. So what happens in two-step reactions is that we're going to go through an intermediate. So here, intermediate. There we go. So it will happen in two steps. First, we will reach a maximum, so that will be my first transition state right there. Then we will get to the intermediate, and then we will have another activation energy, and then finally that intermediate will become the product. So right here, at this point, we're going to have one activation energy, so that's activation energy 1, and then we're going to have a second activation energy 2, right? So the reaction is going to have a step 1 and step 2. Because the activation energy of step 1 is much higher than the activation energy of step 2, that means that the reaction will proceed based on this first step. So this first step will be the rate determining step. So the reaction will go as fast as this first step can go, because this second step is much quicker. So let's look at some examples. So here what we have is step 1 represented. So we have the starting material, the activation energy, and the transition state. Then here we have the intermediate. And here we have the intermediate with a second activation energy becoming the final product. So overall, this is what we're going to see. And there is so much information that we can get from here. So here we can get the 2 activation energies. And so based on these activation energies, we know that the first step is the rate determining step. So the reaction will go as fast as this first rate determining step can go. We also know that the difference between the energy of the starting materials and the energy of the products, it's a negative value. So then this reaction will be exothermic. And we know that we have an intermediate right here. And so this intermediate sometimes will be higher up, sometimes will be lower. It depends on how stable that intermediate is.